I have opened the baby weight data and I'm going to look at doing an analysis of variance to see if there is a difference in the birth weight between the mother's smoking status. So I'm using the process described in Laird statistics. I do like the way they write it up. So the first three assumptions are about your data, and you need to check them based on the design of your experiment and how the data's been coded. So our dependent variable interval ratio, that's our baby weight, and that's continuous. Our independent variable has two or more independent groups, that's our smoking groups, and independence of observations. So we're just going to assume that this is fine, but we don't actually know how the data was collected, so it's a little bit hard to comment on that, but you should comment on it for your own data that you collect. So what we're interested in SPSS is checking these last three assumptions, which are very similar to the t-test. Well, the same, I suppose. So we're looking for no significant outliers, that the dependent variable is approximately normally distributed for each category of the independent variable, and homogeneity of variances, which we can test when we run it. So one of the difficulties with doing ANOVA, I think, when you're getting started, is that these assumptions are a little bit flexible. If it's very rare to get any data that's completely perfect. And so where it says there's no significant outliers, we're really looking to see if there's any that are going to be having a strong pull on the mean, because that's what the ANOVA's testing is there a difference in means. This approximate normality, again, this is not, we wouldn't expect any data to be perfect. So if it looks okay, then it's probably okay to go along with the test, and we'll see some examples of this. So in order to check outliers first, I would normally do just a box plot, because they pop up with a little symbol. So I'm going to drag in a box plot, birth weight on the y-axis, and smoking status on the x-axis. Okay. So we can see that SPSS uses two different symbols for the outliers. If they're not too far away from the rest of the data, it gets a circle. If they're a bit more extreme, it gets an asterisk. So we do have a number of outliers in this data set, and the question is whether or not they're significant. And just looking at it, we can see that I happen to know that we do have a lot of data in this data set, hundreds of observations, and we'll see that when we do the histograms. So these outliers here are actually probably not too much of a problem, just because they're either side of the data and this box is looking a little bit squished. So I think what's happening is that the normal distribution is going to be a little bit what we call kurtotic, and just like it's been pulled up a tiny bit. But I don't think that these outliers will be having a strong effect on the mean. I don't think they're going to be pulling it up or down, or left or right, depending on which way you do your box plots. Sometimes you can put off making a decision until you've done another graph and just weigh them up together and see if you think it's going to cause a problem. So next I would be interested in looking at the normality. Now there are tests for this, however I'm just going to look at it graphically and just make a decision based on how the data looks. If I go to the legacy dialogues and histogram, it allows us to split up the dependent variable into the groups. It's popped up on my other monitor, which is quite convenient, and I haven't quite worked out how to do that in the regular dialogue. So variable, display normal curve, and we're interested in smoking status. Okay. So the big thing that we can see here is that we actually just have a lot more data in the first two groups. So we have a lot more women in the never smoked and the now smoked than in the smoked until pregnancy and former smoker, just by the height of the histograms. Now they're actually looking pretty good. We can see that these are the outliers here that are popping up right in the tails of the histogram, and it's going over the top. So this is where it's sort of normal, but it's a little bit too peaked up here, and then these are becoming outliers here. But I'm going to say that that's not too extreme, and it's probably okay to go. I don't think it's going to affect the results of the analysis of variance. So the last assumption of the equal variances, just showing, so that's saying that equal amount of variance within each of the groups, and they look fairly evenly spread out here. It's a little bit difficult to assess visually because we can't actually see the variance itself on a box plot. We can just see the spread of the data, and sometimes outliers can have a little bit of an effect that you can't see clearly until you calculate it out. So I would normally run this test of variances, which is quite easy to do when we do the analysis. So under Analyze, compare means, intuitive, that's probably the word I was looking for. I don't think variances are quite so intuitive, so that's why I would test them. Way Anova. So we're interested in birth weights and smoking status, options. So this is where we'd probably want our homogeneity of variance test. Now you can get a means plot out here. I believe this one doesn't have the confidence intervals on it, so I don't like this one. I prefer to do my own means plot at the end. It's possible you might want some descriptive stats out. I'll just continue there. Now the post hoc options, this is what we need if the ANOVA tells us that one of the groups is different, or at least one is different. We need to know which one is different. And the way of testing that is with these post hoc or after the fact multiple comparisons. Tukey's is a common one, and that usually works fairly well. Some resources will say it's a tiny bit conservative, so if it's telling you there's no differences when you think there are, you could move to one of these other tests, but I think in most cases Tukey's will do fine. So I'll just leave that there and press OK. So let's take this output a bit at a time. So first up we've got this test of variances. So the null hypothesis is always that there is no difference, and for a test of variances it's that there is no difference in the variances between each of our groups. We've got no evidence to reject this, so the significance is quite high. So this means it's okay to continue with the test. So then we'd move on to the ANOVA. The null hypothesis for the ANOVA is that there is no difference in the mean birth weights between babies born to different categories of mothers depending on how they smoke. We've got a highly significant result telling us that at least one of the means is different from the other, but that's all that ANOVA tells us. It doesn't tell us which one is different. So that's where we can look at the multiple comparisons. You get two versions of the output. In most cases they match up. On very rare occasions they don't match up between this output and the homogeneous subsets, or homogeneous subsets depending on where you come from, and that's where you might want to run a different test, but in most cases this will be completely fine. So this is Tukey's honestly significant differences, and I feel like this is probably the easiest output to understand. We are getting a little warning here that the group sizes were unequal, so they're not guaranteeing the type 1 error level. So it's just saying that it's not guaranteeing the p-value here because there's such a difference in the sample sizes. So we had 481 women in the now smoked group, 533 in the never smoked, and only 94 in the smoked until pregnancy, and 103 former smokers. So that's our sample sizes here. And we could see that on the histograms. We could see that there were a lot more in these groups than there were in these two. So what is this telling us? The homogeneous subsets is putting categories together which are similar. So if categories fall together in a column, it means they are similar. So it's saying that the mean birth weight is similar for never smoked, smoked until pregnancy, and former smoker, 122, 122, 124 in ounces, which I can't convert to grams in my head. And then the now smoked group is lighter on average, which if you've read any of the literature on smoking in pregnancy, this probably won't be a surprise to you. If you have trouble interpreting this, then I'd really suggest you do a graph, and actually, to be honest, I usually do the graph first so I know what I'm looking for. So the test is about the means, and the graph we want will be the means and the confidence intervals. So if we go into Chart Builder, it's under bar because they're error bars, and if you've already done your box plot, you can just drag that over the top and it will switch out the box plot for the means and confidence intervals. Now you can sort of see that the now smoked is lower than the others. Actually, I think what might make it easier to see is if we change the scale on the y-axis, just to zoom in a bit. So to edit the graph, just double click, then double click again, and then click on the bit you want to change. So I've gone through 3 levels of clicking here. Oh, didn't quite get it. And just watch where that yellow highlighting is, because that'll give you a clue as to what it's going to let you change. Then it says scale, Now I don't want the minimum to be 0. I'm going to bring that up to, well, let's say 100 actually, and see what that looks like. Close. So now we can really see the difference here, and sometimes it's helpful if you really want to see the difference between the confidence intervals just to add a reference line. You can move that around and perhaps even change the colour so it's not so intrusive. Although if I start changing colours, I'll have to change all of them because I hate them so much. A little distracting. Anyway, so what we can see is that the now smoking mean is much lower than the other three. So in the multiple comparisons up here, it's said that these three are similar to each other, and effectively it's like drawing a graph, getting out a pencil and going, look, these three are similar to each other. All the confidence intervals overlap by quite a lot, and so we would expect that there's no significant difference between them. However, the now smoking is clearly the one of the rest of the pack, and that's why it gets its own group here. If the confidence intervals overlap a little bit, it's possible that the difference is still statistically significant. You really have to check the p-values for that. If they are completely separate, then it's definitely significant. I find using graphs quite helpful. If you're not sure, you can look at the other output where it does every comparison 2 by 2. So now smoked with never smoked with now smoked, significantly different. Never smoked compared with smoked until pregnancy, no difference. Never smoked until former smoked, no difference. So the null hypothesis in each of these cases is that there is no difference in the means, well, the population means. So you can go by those 2 by 2, or you can look at the subsets, and I suggest at the same time you also look at a graph just to confirm that what you're reading matches up to what the data look like.